Today I am going to discuss about simulated annealing. My name is Annealing Gupta. I am pursuing BTech and MS by research in CS from IIIT Hyderabad. So simulated annealing is basically a local search optimization technique used to find global optima of a cost function. So by definition, simulated annealing is a probabilistic technique to find global optimum of a function that may possess several local optima. It is a meta heuristic for approximate global optimization in large solution space. I would like to mention that simulated annealing is better than its counterpart like hill climbing because it doesn't get stuck on local optima. So the intuition behind simulated annealing, it's based on annealing in metallurgy, where the solids are heated to their melting state, in which their irregularities can be removed quite easily. But as it cools down, the structure becomes rigid and the changes are not easy. So we apply this intuition by allowing occasional ascent in the search process, therefore being able to escape the trap of local minima. So the characteristics simulated annealing uses is iterative improvement. So we move on to the better solution from the current solution in each iteration. Local random search, it looks for the better solution in its neighborhood. Greed simply accepts what's better. So the behavior of this approach, in early search we try to explore the solution space. We may accept a poor state early on in the search process, but as the search progresses, the simultaneous annealing becomes greedy and it's less likely to accept a poor solution. So how does temperature controls the acceptance of a solution? So we define the change in energy delta as energy of new state minus energy of current state. So we basically want to minimize the energy. We want to find the global minimum energy of all the states. So a descending state step is a step in which delta is less than 0. So the energy of the new state is less than the energy of the current state. So we are going to always accept that state because it's better. But in ascending step, the energy of the new step would be greater than the current state, so the delta would be greater than 0. For that we accept only if it passes the random test. In random test we define the probability of the new state as exponential of change in energy by temperature. If it's greater than a value between 0 and 1, we accept that state or we continue the process. So the cooling schedule, annealing temperature is the parameter that controls the frequency of acceptance of ascending steps. So basically, more the temperature, more the number of acceptance of ascending steps. So we gradually reduce the temperature. At each temperature, search is allowed to proceed for a certain number of steps. Let's move on to the algorithm. So at each iteration we compute the energy difference from the new state to the present state. So if the change is negative, that is the energy of current state is greater than the energy of new state, then we accept it. Else we apply the random test. In the random test we compute exponential of change in energy by temperature, and if it's greater than a random value between 0 and 1, we accept it. Then we reduce the temperature. We repeat this process for certain number of times. uh, we stop when the temperature is less than a particular threshold. So at each temperature, um, the temperature so at each step the temperature is decreasing. So the expression exponential of negative of delta by temperature is thus becoming more and more less. So the probability of acceptance poor state is becoming more unlikely. So that's mainly the algorithm. So what are its effects, which are desired and not desired? So the desired effect is that it helps to escape the local optima. The acceptance of poor states in the early on in the process allows us to escape from the local optima. But the adverse effect is it may even pass the global optima. So that's the consequences of occasional ascents. That's it.